subject. I have taken the topic for this demo session. It's closely related to both of our interests. So one is propulsion, and another one is gas dynamics. So today I'll be briefly discussing about the one of the most important part of the aircraft engine, that is a diffuser duct or intake. And if time permits, I will also explain a little bit about the uh, exhaust nozzles. So these are pure combination of our theoretical understanding of the subject and just flow physics to take over to do the engineering job. So we are not adding any moving components or nothing like that. So we are just allowing a shape, an aerodynamic shape, to do the job. So it's a very interesting ideas. So whenever if I say like an intake or a diffuser, what comes to your mind? You guys must might have encountered this terminologies before in your engineering. So can anybody just tell me what is a diffuser is? Okay, so let me explain in this fashion. So diffuser or an intake, it is a duct through which, when the flow moves, the kinetic energy will be converted to a pressure energy. It's the simplest way to explain in an engineering terminology, right? So, but we have studied from our aerodynamics, or maybe from your gas dynamics, if you guys have studied it once. So you saw that when you have a subsonic flow, right? 1 second. This pen is okay. So when you have a subsonic flow, what is subsonic flow? The Mach number that is less than 1, right? So when you have a flow, something like that, when it enters a duct. So to bring the kinetic energy down, or to decelerate the flow and increase the pressure, then what we have to do? We have to have a duct so that is diverging. So how do you conclude that one? So you might have studied this very interesting area Mach relation in your basic gas dynamics. dA by A should be equal to something like m square minus 1 times du by u, kind of thing. So you can see, so if you take any two cross sections, so what's happening? The area is increasing in this case, right? So now if I want to decrease the velocity, so that means u2 minus u1 should be less than 1, right? So that is what the deceleration means. So if du by u2 minus u1 is less than 1, so if Mach number is already less than 1, so subsonic case, so then what happens? So this is negative, this is also negative. So negative times the negative is positive. So that means dA by A has to be positive. So like greater than 0. So how it can happen? So that means A2 minus A1 should be greater than 0, or that means A2 should be greater than A1. So if I take two sections, 1 and 2, right? So it dictates us, the flow physics dictates us, if I have a subsonic flow, then if I want to have a deceleration in the duct, so that means the area has to increase, right? So the same argument you can go on and do it if you have a supersonic flow. So supersonic flow in a duct. So then what should be the shape of my duct so that the flow decelerates? So the same argument you do there, but in that case, here Mach number is greater than 1. So that means this quantity is positive and this quantity is still negative because we want deceleration. So that means the overall quantity becomes negative. So that means this argument now A2 minus A1 is negative. So that means A2 is less than A1. So that means I have to have a converging duct, right? So see, so very beautiful. Just the flow physics is telling us how the shape, that's the geometric shape of a duct should be if I want to decelerate the given flow. Any doubt here? Okay. So yeah, so of course I did not make an effort to derive this area Mach velocity relation, but in our regular classes we will be dealing with these derivations too to understand the physics much more clearly. For now, let us take this as a formula that is granted. Okay, but okay. So the another important aspects of intakes or diffusers is like, yeah, we understand we want to decelerate the flow and make the available kinetic energy into some sort of a pressure energy. We are increasing the pressure and all, but that is not the primary purpose of a diffuser. So the primary purpose of a diffuser is to have a uniform flow at the entry of a compressor, because if I take an entire engine, let me just go to one page previous slide so that like I can get a better space. So here you see, if I take an engine as a whole, right? So say like from here to here, I might be having a intake section. Then what I have, I'll be having a compressor section. Then that compressor is connected through a shaft to a turbine. Then I'll be having a propelling nozzle afterwards. So the flow exits. So flow enters like this, flow exits like that, right? So here I might be having a combustion chamber between compressor and turbine blades, right? So the idea here is the intake ducts are meant to bring the flow, that is, say like if you the air, this is attached to an aircraft, right? So the in general we'll be having an aircraft. So you might have seen the aircrafts, right? Like commercial aircrafts, like where if you are flown somewhere um, through Indigo or those airlines. So you have seen where the engines are attached in the aircraft. Below the wings, right? So you might have seen the engines are attached somewhere like this, right? So this is again a very beautiful idea. Where do you have to attach? So this interesting this entire structure is called uh, a pillion. But the thing is, where do you attach? So it's again your fundamentals of fluid mechanics or aerodynamics that you study, like you study Rankine half bodies and all, right? So if you have a source and a uniform flow, they are kept together. So you find Rankine half bodies, the flow like this, right? So these shapes are made using those Rankine half bodies, and this is a very interesting concept that I don't want to jump into, but I'm just giving you an uh, fruit for thought, right? So how the pure mathematics that you study in your aerodynamics classes can be applied to a real world engineering. So these flows, the potential flow theory is a mathematical way to look at the flow, right? So inviscid, irrotational, everything. So it's not a realistic flow. This is a very much of a modeled flow. But from there, like you can actually, so like if you find out the distance between this stagnation point and this source location, so you can always find this one to this ratio, the maximum height, how much it can reach. So S by D, let us take. So this S by D, how much should be, so that I can have a flow, the uniform flow that doesn't feel the disturbance, right? So that is the whole idea. So I don't want a flow that is coming at this location to be disturbed when it reaches the engine. So that is a very important concept. So I want to make sure this S by D has to be such that the disturbance is kept below the certain level. Okay, yeah. So that is the discussion for another day. So, but let us see. So the engines are attached to the wing, right? So now all my interest is, since we know the aircraft is moving at a velocity, some velocity u say, and the outside ambient conditions, the atmosphere, that is a stagnant. That's what we assume, right? The aircraft is moving into the stagnant atmosphere. So when we study our physics in class, so what we make aircraft to be still and the flow to come from the other direction. So at the end of the day, the in the aerodynamics, what matters, the relative motion between the object and the fluid, right? So that is very important. So the outside ambience, whatever we are having, it might not have a smooth flow. Like if you are doing the computational analysis or the wind tunnel experiments, there what you do, you have a controlled environment, right? So you provide a very nice wind tunnel section, then you test your model. So it's like place an engine in the test section. So what you are making, you are borrowing the air from the ambient and allowing it to come to a streamlined motion, right? A uniform, nice uniform motion. But this is a very controlled environment, laboratory thing. But when you look at the realistic scenarios, what happens, in reality, you don't get that uniform flow, right? So first of all, aircraft is moving, it is a relative motion. So on top of that, your atmosphere might not be so uniform. So the velocities that enter, the velocity at which the fluid is entering to the engine might not have an uniform profile, right? So when I say the uniform flow, what does it mean? Can anybody tell what is uniform velocity means? This you must have studied in your basics. No turbulence. Okay, yeah, so I can take that as an answer. Turbulence is again an involved topic, so I don't want to touch that one. But yeah, so I can take that as an answer. So uniform velocity, all it means is I will have a constant velocity at any given cross section, right? So see, like this is your engine from a side view. So if I make this view a front, so it might be something like a circular section. So when I measure the velocities at any given point in this cross section, any point, say, so that velocity, magnitude and direction has to be same, right? So that all it means, right? So if I take the profile, say like this section I am drawing here, right? So if I drawn this section, along which if I plot the velocity, so it should look something like this. So r let me call it as ry is equal to minus r2 plus r. Somewhere in the center it is 0, right? So if I draw from this to this one, so if I make a velocity plot, so this is my velocity. So this velocity and this velocity are anywhere between the this minus r to plus r, that has to be same. That's what it means, right? So constant velocity, that's what we mean when we say uniform velocity. But the idea here is, so the flow that comes from the atmosphere, that might not be an uniform, so that is understandable in realistic scenarios. So there will be lot of non-uniformities that is present. So very very important. Why? Because our compressors are designed, the later parts, these compressors are designed such that when the flow enters to the compressor, it has to be uniform, so then only it can give me an optimum performance. So like think like this, like you are getting zero velocity at certain parts, and 50 meter per second at certain points, and 100 meter per second at certain points, so that that flow is entering to the compressor. So we cannot expect the compressor to behave as a compressor in a optimum fashion, right? So we have to make sure from root to tip of the blade of the compressor is seeing the same velocity. So that is the whole idea. Okay. So that is why, so all these disturbed flows, we are making it uniform through a intake ducts. So that is the primary purpose of designing an intake duct. Okay, so the increase in pressure, the deceleration of the flow, they are all they are not the primary purpose. Of course, we are doing it, but they are not the primary purpose. The primary purpose is to make sure the compressor sees a nice uniform undisturbed flow. Everybody clear? Okay. So now if I come back to the idea of the intakes, right? So we understood why the intakes are important in an aircraft engine, right? So now we can do the formal analysis, because like this topic is taken from the middle of something. So I did not give you the proper context before these topics, whatever we are going to discuss. Before this, like I usually discuss about the ideal cycle analysis. So that is where we start, and I will bring you the idea of stagnation properties, like how formally we define the stagnation properties rather than whatever you see in the textbook definition. That is not a full-fledged definition. Uh, but like all those things needs to be discussed before moving on to the topics, something like this. But so like let us assume those all things that we already done, and let's just move with this. Okay. So now the next formal analysis for a diffuser is like we have to quantify certain things. So what do we quantify? That is an efficiency of the diffuser. So how efficient is my intake or the diffuser is? So that's what we are going to analyze. So why the efficiency comes here? Because in realistic scenarios, though we assume in the diffuser, we can model the flow with any of the assumptions, inviscid, incompressible, or like in inviscid, irrotational kind of idea. What does those terminologies means? Those terminology means that we are having no friction in the flow, so that there is no loss, and there is no rotation to the fluid, so that there is no vorticity kind of thing generated, all these things. But in realistic scenarios, this is not the case. And from the thermodynamic point of view, what we assume, the process is adiabatic, right? When we analyze a flow through ducts, so that means like there is no work transfer, there is no heat transfer across the boundaries. Okay. So all these things we assume while modeling the flow. But in realistic flows, no, it is not the case, because the friction is inherent, right? Like whenever I have a body, the solid body, so the flow has to see the boundaries, right? Solid boundaries. So we know that there is a no slip condition. So that means the relative velocity between the fluid and the geometry has to be zero. So that means there is a friction that is generated due to the presence of the body. So that will bring in the inviscid problems, sorry, viscous problems. So those viscous problems will cause the boundary layer to form. So all these things, like, we are not going to discuss in detail now, but in reality, so we do encounter a losses due to viscous actions. On top of that, we have studied, so we are in the deceleration region, right? So u1 and u2, if I take, so u2 is less than u1. Also, if I take pressure at this section p2 and pressure at this section p1, so p2 will be greater than p1, right? So that means, so we are in an what we say, adverse pressure gradient region, because p2 is greater than p1. So the flow is going against a pressure, right? So in general, the naturally our flow will happen from high pressure region to low pressure region. That is how the general physics governs us, right? So the pressure difference is going to drive the flow, so in general. But here, what we are making is like the flow to go against this. So that means it is under adverse pressure gradient. So we don't like, because of this, and the because of this viscous action near to the boundary, there is a boundary layer that is formed, so that can easily separate. The separation of boundary layer is very likely in the diffuser sections. So this is going to be a very, very big problem in an actual design. Okay, so we have to design our intake such that it is not going to, the flow is not going to separate, as well as we are making sure the uniform flow exists at the end of the diffuser duct. So this is very, very critical, like these 2 points. So that is very challenging, that is why. Okay, so now what we model is using nice adiabatic flow model, but in reality there is a this reversible sorry, irreversible losses that you cannot easily quantify. So that is why what we do, so we rely on this efficiency definition. So how much efficient is our intakes? So this is where the efficiency comes into picture. So this is very interesting, how we do the efficiency of a diffuser duct. Let us just formally do it. So here we are going to do the thermodynamic analysis. So I am plotting the TS diagrams. So TS diagrams is a very nice way to quantify gas turbine engine analysis or the performance. So let us say I am at an ambient condition. So in TS diagram, so I am just locking my position first at the intake. Okay, some entropy level S1. Select, let me call SA, TA, and how the pressure lines looks in TS diagram, like this, right? So they are diverging curves, constant pressure lines. Okay, so this is my pressure PA at the entry. So all these conditions are at the entry. PA, PA, S1, everything. All right. So now, if the assume if all the process happens in a theoretical fashion, that means ideal way. So then we would expect the entropy to not change, right? So it's a constant entropy, isentropic, adiabatic, and reversible. So that is a most idealistic scenario we can think of. So that means this would be my P naught A. That is an ideal isentropic pressure. Okay, so again, I did not define what is total pressure, total temperature, and all. Formally in the class, we will define these things before coming to this point. Let us assume we know that. What do we mean by? Okay, so P naught A, and the corresponding temperature would be T naught A. Okay, but we know for a reason, because of the loss. So the in the realistic scenarios, that is a viscous flow. So this P naught A is not equal to the actual total pressure at the exit of the intake. So that is P naught 1. So that means I'll be having a new condition over here, P naught 1. This is actual total pressure at the exit. So this is ideal P naught A. Okay. So now you see, so this is the actual state now, right? Why T naught A and T naught 1, sorry, in this case, yeah, so let us call it as station 1, station A, station 1. So T naught 1 are same because we are still in the adiabatic region, but irreversible. So it's not isentropic, but still it's adiabatic. So adiabatic, we know T naught is constant for steady adiabatic flow. So T naught is constant. Okay, but P naught may not be. P naught is constant for isentropic, but not for all general adiabatic. Okay, so now the assumption now is, what if the the pressure change that would have occurred from PA to P naught 1, this is the actual pressure, occurred isentropically. Not this one would have been the highest possible case in reversible fashion. But in irreversible process, we somehow got into P naught 1 with this P naught A minus P naught 1 being the loss. Now you have P naught 1. So now the question is, what if my diffuser is raising the pressure from P naught, sorry, PA to P naught A, that means decelerated the flow, right? So this much, so let me call it as C1 square divided by 2CP, right? So that is the difference. So now it raised to this point only through an isentropic process. What if? What if? So ideally, I would have raised from this point to this point. This was ideal, and this was actual now. So that ratio is what we call it as the efficiency. So that means the diffuser efficiency, I am writing it as T naught 1 minus TA divided by T naught A. This one I am not calling T naught 1. So let me call it as T naught 1 dash, because this is not T naught 1. T naught 1 is this one, right? So this is T naught 1 minus TA, right? So this is an hypothetical point. So that means like we are just extending this pressure line and we are meeting at constant entropy line, and see what if this actual pressure is reached through an isentropic process. So that is why this temperature T naught 1 dash is different from actual temperature T naught 1, right? So this is the definition. So now I can use the isentropic relation between these 2 points because they are falling on constant entropy line. Again, I am not discussing the constant entropy line and the isentropic relations, but that we formally derive in the class before coming to this point. So that means if I take TA common here, so that becomes T naught 1 dash by TA minus 1 divided by, this is again T naught 1 minus TA. That one I can also write it as T naught A minus TA, right? Because T naught 1 and T naught A are same. So see now, this one I can represent in terms of pressure. That is, this falls on P naught 1 line and this falls on PA. So using the isentropic relation, T naught by T is equal to P naught by P to the power of gamma minus 1 by gamma. So that I can use here. And again, from the gas dynamics that you guys study, that I can write T naught A by TA using the Mach number. That is 1 plus gamma minus 1 by 2 times MA square. MA being the Mach number at the entry of the engine. So this one, right? So that you can replace over here. So 1 plus gamma minus 1 by 2 MA square. And again, there is one more 1 that comes over here. If I take TA common, both the side, this becomes TA minus 1. So TA cancelled. So this one I am writing in terms of pressure ratio. This one I am writing in terms of Mach number. If I just go to the next page, so I can write if efficiency of a diffuser is equal to P naught 1 divided by PA to the power of gamma minus 1 by gamma minus 1 divided by gamma minus 1 by 2 times MA square. Right? So this is what we end up as the definition. And we will also define one more parameter called pressure recovery factor. So pressure recovery factor is nothing but how much of pressure we have recovered from the original stagnation pressure. So that is P naught 1 divided by P naught A. So this is the maximum pressure we would have got, but we got only to P naught 1. So that is a pressure recovery factor. So sometimes in the questions in GATE, either they will ask you to calculate the efficiency of the diffuser, or sometimes they will ask you to get the pressure recovery factors, or like these datas are given alternatively. Sometimes they give pressure recovery factor instead of this ratio. So all these things like they can play with those numbers. But like once we have like once we understood the different variables, so then it is not going to be that difficult for you to tackle this problem. It's only going to be tricky but not difficult, right? So this is um, what the problem is. So now we have a definition for diffuser efficiency. So since it's a demo class, I don't want to go into the further details on the diffuser section. Let us just see one or two questions from previous year GATE, right? So that makes our life simple, so that like we will understand what's going on. So like formally, if you plug in these two conditions, so we should be able to get to this form. The pressure recovery factor P naught 1 by P naught A can be written in this fashion. But let's not go into the details of that, like because like we already have a efficiency, that is P naught 1 by PA power gamma minus 1 by gamma minus 1 divided by, that is gamma minus 1 by 2 times MA square. So if you just rearrange that one, so what it becomes, heat of diffuser times gamma minus 1 by 2 times MA square plus 1 is equal to P naught 1 by PA to the power of gamma minus 1 by gamma. I am taking to the other side. So that becomes gamma by gamma minus 1. So now we know what is P naught 1 by P naught A. So P naught 1 by P naught A can be written as P naught 1 by P1 times P1 by P naught A, something like that. Or you can also write P naught 1 by PA times PA by P naught A. So this one we just calculated. So you plug in over there PA by P naught A. We can always get it from isentropic relation because we are defining at given point. So we can always use. So we can actually calculate, right? Okay. So let us just take one of the gate questions on the diffuser topic. Yeah. So can you guys attempt this question based on what we discussed so far? Says like the diffuser of an airplane engine decelerates the airflow from the flight Mach number 0.85 to the compressor inlet Mach number 0.38. Assume that the ratio of the specific heats is constant and equal to 1.4, if the diffuser pressure recovery ratio is 0.92, then the isentropic efficiency of the diffuser is. It is very, very interesting problem. So whenever we get a question like that, like the best idea to start is do the control volume model of the given problem. Say like I have a diffuser. So why it is diverging duct? Because the Mach number is subsonic, right? MA, let us say, that is equal to 0.85. So subsonic. So I should have a diverging duct. So M1 at the exit of the diffuser, I have 0.38. Okay. So now they are also given the gamma 1.4, the ratio of specific heat. Also, they are given the pressure recovery factor. So what is that one? So this is my actual pressure P01. This is my ambient pressure PA, correspondingly P0A. So P01, the corresponding static pressure is P1, right? So they are given P01 divided by P0A is 0.92, right? So then what else? Yeah, so that's more than sufficient. They are asking what is the efficiency of the diffuser. We just derived that efficiency can be written as P naught 1 by PA to the power of gamma minus 1 by gamma minus 1 divided by gamma minus 1 divided by 2 times MA square, right? So this is already given to us. MA is noun, but we don't know what is P naught 1 by PA ratio. So how do we calculate that one? So I will calculate P naught 1 by PA. So like P naught 1 by P naught A can be written as P naught 1 by PA times PA divided by P naught A, right? So I can always write P naught 1 by PA is equal to, so just rearrange it, is equal to P naught 1 divided by P naught A multiplying P naught A divided by PA, right? So this is given to us 0.92. And how do we calculate this one? This one I can calculate using isentropic relations. So that means this I can write it as 1 plus gamma minus 1 by 2 times MA square to the power of gamma by gamma minus 1. So I can replace that one with the isentropic relation. MA is given to us 0.85. So in that sense, we should be able to calculate everything, right? So if we substitute back over there and calculate what is P naught 1 by PA and what is all other things are given to us. So we should be able to see the diffuser efficiency to be 0.814. Okay, so I'm not going into the details of the algebraic manipulations here. I've just shown you the steps how we get it. So you guys can verify it if you want, right? Everything is with you. So like you just have to put this 1 plus gamma minus 1 by 2 times MA square, rise by gamma minus 1, multiply with 0.92. So you should be able to get this number. And again raise the gamma minus 1 by gamma. So don't forget that, right? So then minus 1 and divided by this numbers. So everybody clear? This is how the actual gate question would look like. From our discussion you should be able to attempt this, right? Any doubt or anything you guys want to ask? Okay, yeah, in that case like we can actually wind up this session. Yes, this is sir.
Yeah, Akshay sir.
Yes, sir. So yeah,
Yeah.
so like I'm done with the
Okay, you
topics.
are done with
Yeah,
demo.
yeah.
Okay, okay. So fine. So guys, any question? Guys, any questions? Okay. So today you have not planned any PYQ in this session, Akshay?
I did solve one of the PYQs. If I want, like I
Okay.
can go on to one more. But
Yeah, one more you can solve, then we'll wind up because we are
yeah,
having some time.
okay, yeah. So then what I do is like I will solve one more PYQ that is slightly from the same topic but different idea. Okay. Yeah. Let us try to solve these questions, guys. So this one is the ideal static pressure coefficient of a diffuser with an area ratio of 2 is. That's what they are asking. See, um, I deliberately took this question in this PYQ because this looks a problem from diffuser straight away, but it is not exactly from whatever we have discussed so far. So that is why sometimes it is very easy for us to get confused, right? So I like this problem in a sense that it's a very interesting fundamental problems to look at. Say I have a diffuser and all they are given in your case is this area ratio. Say like this is A1, this is A2. So they are given an area ratio of 2. What does that mean? A2 by A1 is given it as 2. This is given. And asking you to calculate the static pressure coefficient. What is a static pressure coefficient? So they are also mentioned ideal static pressure. So what is a static pressure coefficient that you guys have studied in your aerodynamics, right? So you define it as Cp. So that is nothing but P2 minus P1 divided by half rho 1 V1 square, right? So this P1 can be P infinity in most of the cases, right? So this is what they're asking. So it looks like just by the word diffuser, you should not get confused with like how to solve, right? So this one should be attempted from a pure aerodynamics point of view. So see, like if I have a flow that is coming over here, so let me just take along one of the streamlines. So like this is the point one and this is the point two. All I'm interested in this one, I can use the Bernoulli's equation. So that is, I know it is ideal. So I'm just assuming there is no losses involved. So P naught can be written as P1 plus half rho 1 V1 square should be equal to P2 plus half rho 2 V2 square. So the one of the things that is missing in the question is like they should have mentioned it's pure incompressible. So in that case, I can assume rho 1 is equal to rho 2 for pure incompressible flow. That is missing. So in that sense, this question is given as a grace because that information is missing. They should have mentioned it. It is incompressible, but it's say so. Still, we can solve it. It's very good problem. So now I can just write for P1 minus P2 from this one is equal to half rho 1. So I'm just taking it as constant, or let me write it for P2 minus P1. Half rho 1, just shift to the other side, this to this side. So that becomes V1 square minus V2 square. And from the basic idea, the mass flow rate is constant, a continuity. So that gives you A1 V1 should be equal to A2 V2 for a constant density, right? So that means I can write A2 by A1 is equal to V1 by V2. So if I take V1 common here, so that becomes half rho 1 V1 square is equal to 1 minus V2 by V1 whole square. Right? So now V2 by V1, I can write it as A1 by A2. So that means P2 minus P1, I can write it as half rho 1 V1 square times 1 minus 1 over 2 square. So that is 1 minus 1 over 4. That is nothing but 3 by 4. Right? So that means half rho 1 V1 square times 3 over 4. Right? So now you substitute this P2 minus P1 back over here. So what happens? That is half rho 1 V1 square times 3 over 4 divided by half rho 1 V1 square. So this and this get cancels. So I am left with 3 over 4. So 3 over 4 is what? 75%, 0.75. So option C, right? So this is a very, very interesting problem. But just by looking at the word diffuser, you should not get confused like we have to address from the efficiency ideas. So I always say it is important to know where to use the formulas that we study in the class, but it is at most important that like where we cannot use, like to know where we cannot use the formulas, the limitations. That is also very important, right? Or else like you will be spending so much time in gate to address these kind of problems in the first place where you cannot have approached in that fashion. So you approached in the wrong way and you will be spending more time to address that problem. So if you don't know where to use some certain formulas, right? So in the process you will be losing a lot of time that you could have used to solve some other problems. So these all things happens, right? So now any doubts, any questions so far from whatever we discussed so far in the session?
Any question, guys? Puneet, Vijay, Yash, Diksha, Akshay, Aditya. Okay, so guys, again, this is another essence of IGC classes, and those who are watching this session. So IGC will make sure you guys learn from scratch and you guys learn each and everything. Okay, during your gate preparation, and all these things will make sure you guys excel in your future as well. So thank you guys. With this note, we'll wind up this session. On thank you, Akshay, for joining this session, and
Yes,
then
sure, sir.
yeah, thank you guys. So guys, see you tomorrow at 7:30 with another demo session, which is